Hello students, good evening all of you. In previous sessions we will discuss some problems on basicity of amines and acidic nature of carboxylic acids, that means ortho effect, and some acidic nature of some organic compounds without carboxylic acid group and phenolic group and alcoholic group. Okay, now here finally let us discuss the acid base reactions. So organic compounds are acting as acids. Okay, so here the reaction of those organic acids with sodium or sodium hydride or sodium hydroxide, sodium amide and aqueous sodium bicarbonate. Okay, so here for a actually it is a overall acidic nature of organic compounds. Okay, it's a overall acidic nature of organic compounds. It is a sulfonic acid is more acidic than the carboxylic acids, and your carboxylic acid more acidic than the carbonic acid H2CO3. Okay, this one is the H2CO3 carbonic acid, and here phenol is the less acidic than the carbonic acid, and it's a water, and here water is more acidic. That means here alcohols are the weaker acid because alkyl group is a plus I group, so here plus I effect to decrease the acidic nature. And then here acetylene and least one is the ammonia. So actually here sp carbon is a more alcoholic than the nitrogen, that's why that acetylene is a more acidic than the ammonia. So very important point here. This acetylene is a stronger acid when compared to ammonia because this is the sp carbon. Okay, that is more alkylative than the nitrogen. Okay, so now here let us discuss the reactions of these acids with the bases. Okay, they are the acids. So first here I am taking this acetylene. Okay, this is the acetylene. So here this acetylene on reaction with sodium actually. Here sodium is the alkali metal. Sodium is a alkali metal. So here they are the acidic hydrogens. So here acid base reaction takes place, NaCNA, and here H2 gas. Okay, this is the H2 gas. Here production of the H2 gas. There is a successful acid base reaction. This one is a basic part. Here in this case there is a acidic hydrogens in a acetylene. Now here it can also react with sodium hydride. So hydrides are basic in nature. So here in this case again NaC triple bond CNA plus H2 gas. Okay, that's it. So in this case of course here 2H2 gas. Now here this one on reaction with the sodium amide. Okay, NaNH2. This is also known as a sodamide. This is also known as sodamide. So here the product is NaC triple bond C Na. Simply we can write this one Na2C2. Okay, Na2C2 plus here this NH2 minus, Na plus NH2 minus. This NH2 minus remove the H plus. Okay, so that becomes a NH3. So it produces a ammonia gas. Okay, it produces a H2 gas. So based on the properties of the H2 and ammonia, we can identify this is a this compound having a acidic hydrogen. Okay, so here in this case this one on reaction with NaOH. Okay, on reaction with the NaOH, NaC triple bond C Na. Here OH minus, if remove the H plus, that becomes a H2O. But here this reaction is not possible. Here this is not a forward reaction. Here the backward reaction takes place. Why? Because this H2O is more acidic than the acetylene. Okay, from this order H2O is a more acidic than the acetylene. So H2O more acidic means your rate of backward reaction increases. Okay, here forward reaction does not take place. Your backward reaction takes place. Okay, because it is H2 is a stronger acid and this acetylene is a weaker acid when compared to water. So when compared to water, if it is a weaker acid, conjugate base is a strong base, and H2 is a stronger acid and conjugate base is a weaker. So sorry, conjugate base is a stronger acid, stronger base, and here stronger acid when compared to acetylene. So here backward reaction takes place, but not forward reaction. NaOH. Okay. Now here this one also does not react with sodium bicarbonate. Here sodium bicarbonate is not decomposed by the acid acetylene. Okay, so here in this case also NaC triple bond CNA. Here HCO3 minus, if accept the H plus, that becomes a H2CO3. That means here H2CO3 is a weaker acid or stronger acid when compared to acetylene. So backward reaction takes place. There is no forward reaction. Okay, that's it. Now here I'm taking alcohol. I'm taking alcohol. So this one reaction with the sodium, that gives a RONA, sodium alkoxide plus of H2 gas. Okay, it's a successful acid base reaction. Now here reaction with sodium hydride. So RONA plus H2 gas. H minus remove the H plus acidic hydrogen from the alcohol. Now this alcohol also can react with a strong base, that is a sodomide. Okay, produce ammonia gas. Okay, but here no reaction with the NaOH because conjugate acid. Your OH minus is a base, so H2 is a conjugate acid because that accept the proton, so it is a conjugate acid. This acid on the product side is a stronger acid than the alcohol, so a rate of backward reaction takes place. Here no forward reaction, and similarly no reaction with sodium bicarbonate also. Okay, because the carbonic acid again stronger acid than the alcohol, so there is no reaction with sodium bicarbonate. It means here sodium bicarbonate cannot be decomposed by the alcohol. Okay, now next reaction of the phenol. Okay, reaction of the phenol with these bases sodium. Okay, there is a reaction, a sodium phenoxide plus H2 gas. Okay, of H2 gas. Now here reaction sodium hydride, they're also same products. Okay, sodium phenoxide and H2 gas. Now here I am taking sodium amide, NaNH2. Okay, NaNH2. Here also same sodium phenoxide, and here that NH2 minus accept the H plus. Okay, so there is a NH3. Now here it can react with NaOH. Okay, the product is sodium phenoxide, and here H2O, OH minus remove the H plus. OH minus remove the H plus. So here H2O is the product. So here in this case, of course, here H2 is a weaker acid when compared to phenol. So rate of backward reaction, forward reaction takes place. Phenol is a more acidic. Okay, here H2 is a weaker acid. So rate of forward reaction takes place. So we can see there is a reaction with the NaOH. Okay, for the phenol. Now here, the sodium bicarbonate. Sodium bicarbonate. Here the sodium bicarbonate cannot react with this one. Okay, sodium bicarbonate cannot react with phenol. Okay, that cannot give the H2CO3. That means H2CO3 is nothing but H2O plus CO2. So there is no efflorescence of the CO2. There is no brisk efflorescence of the CO2. That means here sodium bicarbonate cannot be decomposed by the phenol because phenol is a weaker acid when compared with carbonic acid. Okay, that's it. But okay, but important point is by the presence of the electron withdrawing groups. Okay, by the presence of the electron withdrawing groups, that means here two NO2 groups are present on this compound, and three NO2 groups are present on this compound. Okay, so here 2,4,6 trinitrophenol and 2,4-dinitrophenol. Okay, you know this one, common name of this compound is a picric acid. Okay, these compounds can react to sodium bicarbonate. That means the sodium bicarbonate is decomposed. So here CO2 is evolved. Okay, there is a brisk efflorescence. Sodium bicarbonate is decomposed by the 2,4-dinitrophenol and 2,4,6 trinitrophenol because these are the stronger acids when compared with the carbonic acid. Because why these are stronger acids? Because presence of the electron withdrawing groups, presence of the electron withdrawing group increase the acidic nature. Okay, that's it. So these phenolic compounds, okay, here in this case mononitrophenol no reaction with sodium bicarbonate. Okay, because mononitrophenol is not more acidic than the carbonic acid, that's why mononitrophenol no reaction with sodium bicarbonate. Okay, so this dinitro compound, trinitro compound can decompose the sodium bicarbonate. Okay, and next let us discuss the reactions of the carboxylic acids. Okay, so carboxylic acids are more acidic. Carboxylic acids are more acidic. So RC double bond O, OH. Okay, and sulfonic acids are also more acidic. So here there is a reaction with sodium and sodium hydride, we can see reaction, and sodium amide, we can see reaction, and NaOH, we can see here there is a reaction. And here the important point is sodium bicarbonate is decomposed by these compounds. Okay, they are the carboxylic acids and sulfonic acids are more acidic than the carbonic acid. That's why here this sodium bicarbonate is decomposed by these acids, so produce a CO2 gas. Okay, produce CO2 gas. This CO2 gas is produced from this one. If it is an isotope here, we'll get the CO2 with the carbon isotope 14. Okay, that's it. Now here the one more point is along with the carboxylic acids, one more the specific acidic nature compound, that is squaric acid. Okay, here squaric acid. This squaric acid acidic nature is almost equal to H2SO4. Okay, H2SO4 is a stronger acid, you know that, and similarly this squaric acid is also stronger acid. The squaric acid is also stronger acid, so it can decompose sodium bicarbonate, produce brisk effervescence. Okay, CO2 is evolved by reaction with the sodium bicarbonate, is a squaric acid. Why squaric acid is a more acidic? Because after loss of proton, okay, here two protons are there generally. Okay, so after loss of the protons, here two protons are more acidic actually, equally acidic for the squaric acid, because it is stabilized by the four equal resonant structures. For suppose if it is a one resonant structure, then next resonant structure like this. So here in this case, this one becomes a O minus, here O minus, here in this case pi bond. This one becomes a double bond. This one becomes a double bond. And similarly, we will get the two more resonant structures. Okay, that means in this case like this. So here it becomes O minus double bond O, here double bond O, here double bond. Sorry, here in this case O minus. Okay, this is a pi bond. And one more resonant structure will get, and that means here four resonant structure. These four resonant structures are equal. Okay, that means here four resonant structure have same energy, because all are the oxygen atoms and the carbon. So the negative charge is delocalized on the oxygen atoms only. So that's why your conjugate base is a highly stable. Okay, that's why your squaric acid is more acidic. So that's why that can decompose the sodium bicarbonate also. Okay, and here the one more important point also, that ascorbic acid also can decompose the sodium bicarbonate. Okay, you know this one, ascorbic acid. Okay, double bond, here double bond O, here OH, here there is a OH, and this one. Okay, here generally this is the acidic proton, this is also acidic proton, but here between these two, which is a more acidic one? This proton is a more acidic one. Why? Because if the proton is removed, that conjugate base must be stabilized. Okay, so here double bond O, this one is a O minus, here OH, here this one is a OH. So in this case, this is a OH. Okay. So this conjugate base is more stabilized by the continuous conjugation. Okay. So H1 more active proton than the H2. Okay. So but here when this proton is released, that means here in this case OH, here double bond O, here it is the conjugate base for this proton. So actually here it is stabilized by the resonance with only pi bond. Okay, but there is no minus M effect working with this C double bond O group on this one. Okay, but in this case this conjugate base is stabilized by the this pi bond as well as this C double bond O electron with the drying group. So more stable conjugate base, that's why this proton is more acidic. And here the one more important point, this ascorbic acid also decompose sodium bicarbonate. Okay, this also decompose sodium bicarbonate, release the CO2. Okay, so those are the acid base reactions. Okay, so here in this case the one more important point is for suppose I am taking like this here, pH O minus Na, and here this RC double bond OH. Okay, here the PH OH plus RC double bond O minus Na plus. Okay, this reaction is possible or not. Okay, so in the examination we can see this type of questions. Okay, so this reaction is possible, okay, in forward direction. Okay, this reaction is possible in forward direction. Why? Because this carboxylic acid is the more acidic compound. This carboxylic acid is the more acidic compound, and here phenol is a weaker acid. Okay, phenol is a weaker acid when compared to carboxylic acid. So the weaker acid conjugate base is a strong base. Okay, weaker acid conjugate base is a strong base. So your strong base and more acidic compound are on the reactant side, so rate of forward reaction takes place. Okay, this reaction takes place in a forward direction. Okay, for suppose if you take like this, that means here, so I'm taking this one, RC double bond O Na plus C2H5 OH. Okay, C2H5 OH. Now here this one I am writing like this, RC double bond OH plus C2H5 ONe. Okay, now here this is the weaker acid, when compared to this carboxylic acid. This carboxylic acid is a strong acid, you know this one. Carboxylic acid is stronger acids than the alcohols. So here stronger acid, weaker acid. Okay, so here in this case weaker acid conjugate base is a strong base. Now stronger acid conjugate base is weaker base. Okay, it is a weaker base. So here in this case stronger acid and strong base on the product side. Okay, so rate of forward reaction is not possible. Okay, because in this case on the product side acid must be weaker. Okay, here on the product side, here on the product side a stronger acid. Okay, but here for successful acid base reaction on the product side acid must be weaker. So here this backward reaction not possible, sorry, forward reaction not possible, but here backward reaction is, sorry, backward reaction is possible because it is a stronger acid, it is a conjugate base stronger, because alcohol is a weaker acid, so conjugate base is a strong base. Okay, and here this is a weaker base because carboxylic acid is a stronger acid. So here for acid base reaction the most important point is on product side acid must be weaker. Here on the product side acid is a carboxylic acid, on this reactant side alcohol is a weaker acid. So here rate of backward reaction takes place, forward reaction is not possible. Okay, that's it. So like this we can decide the either acid base reaction possible or not. Okay, so product side you must have the weaker acid. Okay, so it is a stronger acid, so there is no forward reaction, that's why backward reaction takes place. Okay, that's it. For suppose, and one more the previous question let us discuss, we will finish with this one. For suppose I am taking this one. Okay, one compound. Okay, here OH, this is a carboxylic acid group, and this is a C triple bond CH, and one more compound here in this case CH2OH. Okay, so this compound, this is the polyfunctional compound, contains carboxylic acid group, phenol group, acetylene group, and alcohol group. Now here taking here just 2 moles of sodium amide, taking 2 moles of sodium amide. So that means here just 2 equivalents of the sodium amide I have taken and added to this compound. Okay, this polyfunctional compound. This is the base, actually just 2 equivalents are available, and it is a acidic one, it is a acidic one, it is a acidic one, it is a acidic one. But which is a more acidic one? Actually this proton first more acidic, and this phenolic hydrogen more acidic, and here alcoholic group third one, and it is the least acidic. So here by adding limited equivalents of the sodium amide or any base, the more reactive, the more active hydrogens are respond to the base. That means here, so finally we will get the product like this. So here O minus Na plus, and then here COO minus Na plus, and then here CH2OH remains same, and this group also remains same. Okay, just first most acidic hydrogen, two most acidic hydrogens react with the two equivalents of the base. So carboxylic acid group more acidic, so first it react with the base, and then second equivalent react with the phenolic group. Okay, so the acid base reaction. Okay, thank you for watching. Please subscribe my channel, and if you like the video, share the videos to your friends. Okay, thank you.